They are telling to see the YouTube channel.
Oh, YouTube channel, but no, we are adding the live session link.
No, live sessions only I am referring. Mostly that some people are giving calendar link in the calendar, but generally it is avoided giving
And
in the.
you can also find the live session link on the course page. We are also adding the link of the course page. This
Where?
course portal. Okay, let me share 1 second. Just start the recording also.
Where? Which portal, sir? Course portal.
Yeah, course portal.
Where in the supplementary?
No. This important links.
How to see the YouTube channel particular?
Okay, 1 second. I just added this
How to locate particular?
YouTube link.
Go on YouTube, type PDSA September 2023.
Oh.
Search on YouTube, you will find it.
Okay, so when you open the course page, you can click on this course introduction and then general instruction and important links. Okay, now you can see the seat live session tagging list, or this live session link for live session September. You can see you can see the direct this playlist of this term live session.
Okay.
Okay, and another is one seat. This is not a seat. Sorry, course playlist. This tagging list. This is for the previous term. I think this is by mistake. Oh, so there is one seat. We will update this. Actually, same link is added to the both here live session playlist and link for live session September. Okay, but you can directly see the playlist of this term session by clicking on this.
For every subject it will be there like that.
Yes.
Okay. Sir. Okay.
Okay, so those who have not joined the Replit team, I am sharing the link of this Replit team again in the chat. Okay, and those who have already joined, just open the Replit team, and I'm publishing the problem. We have 3 problems today. Okay, so refresh your Replit team page. Okay, so now you can see the total 3 problems, B4 problem 1, 2, 3, and we will start from the problem number 1. Okay, so as you have already learned this BFS and DFS algorithm in the B4 content and topological sort and graph related algorithm, basic algorithms. So now these problems are based on that algorithms. So now you have to figure out, after reading the problem statement, you have to figure out that which algorithm is best suitable for this problem and what things actually we are asking in behind of the story. Okay,
sir.
So just read the problem statement of the problem number 1 and just think about that. If his question is straightforward, then it is okay. Otherwise, some story is actually added to the top of the questions. So now you have to figure out that what things is actually asking in the back end of the story, then figure out that which algorithm is best suitable for this. So now here, the question statement I am reading, the express train routes are provided in the adjacency list. Okay, so here adjacency list is given. The name of the adjacency list is A list. Here you have to find out the route from start to end, okay, with minimum number of hopes possible. Okay, hopes means stoppage possible in the path. So write a function minimum hopes where we are passing three parameter a list, start and end. So here this start and ends are actually vertices. To return the cities to be visited starting from start to end. Return the list with only start if the end is not reachable. Okay, so here adjacency list is given for the graph. Okay, two vertices are given, start and end. You have to figure out that what is the path from start to end, shortest path. Okay, which contains the minimum number of hopes or stoppage in between. Okay, if end is not reachable from the start, then you have to return only start vertex inside the list. Okay, so I hope problem is clear.
So can you explain the example that is?
Okay. So let me just give some example.
That is
So
given there 1 8.
okay. So this is given,
Yeah.
and also this image graph image is also given. Okay.
Yeah.
So this is the one graph is given. Okay, and graph representation is given in the adjacency list form. So there are two representation we generally use: adjacency matrix and adjacency list. Okay, here adjacency list is given, where this node key of the dictionary is actually representing the source, and these elements inside the list is representing the nodes which are connect from the this key. Okay, so here there is one directed as from key to the this nodes which are coming inside as a value of this key. Okay, so if you just relate this graph, so you can see that from 0, so 0 to 8 and 8 to 0 both are the edge. So 0 to 8 is one directed edge and 8 to 0 is also a one directed edge. So now you can see here we are making 0 as a key, and 8 is the node where this there is one edge coming from 0 to 8. Okay, similar for the 8, you can see that there is one edge coming from there from 8, there is one edge going to 0, and there is one edge going to 9. So you can see in the here in graph, so one edge is going to 0 and one edge is going to 9 from 8. So this is a representation of graph in adjacency list form.
How you are opening graph representation?
Graph is visible, my screen is visible.
Yeah, it is visible. For us, we have to click that link given in the question.
So I'm not getting your question. So this is the Replit team.
A list, in the below there is one link like it is given a graphical representation.
Yes.
That you have to click for opening.
No, I'm not opening here. I'm just representing here. Okay, I'm not writing anything.
How do we get it in the Replit page?
Okay. Yeah, so you can click on this MD file. MD
Okay.
file. After that, you can click on this preview.
Okay.
Okay, then click on this preview button, and now you can see the.
Okay.
Okay, so.
Sir, I couldn't get it. How to see that in the Replit page?
In Replit team, you can see the question, and inside the question file, you can see one problem 1.md. Okay, when you click on this problem 1.md, this type of markdown file is open. Now you can click on the top.
Okay.
This eyes symbol preview. Okay, when you click on this preview, so this will be look like.
No, in line number 30, there is one line is given as a graphical representation in the Replit.
Okay.
Replit in the problem. Line number 30. What is this last line?
No, this is a markdown representation, but you can click on the preview button.
Oh, that last line is nothing to do with that.
maybe you did not open, but this preview is will be represent the actual content. Here, this is a raw file.
Okay.
Okay.
Okay, sir. Thank you.
Okay, just explain the things. What is asking in the terms of graph. Okay, so this type of graph is given in the adjacency list form. Okay, one start node is also given and end node is also given. Suppose start node is given 0. Okay, so this is start, and one end is given like 5. Okay, so now you have to find out that what is the shortest path from this 0 to 5. Shortest in the terms of minimum number of nodes in between, or you can say minimum number of edge in between. Okay, so here there is no weights given, so that shortest path with the weights will come in the big 5 content. But here we are finding the shortest path in terms of minimum number of hoops or nodes in between, or minimum number of edge in between. So in that case, which algorithm you can use?
BFS, sir.
BFS.
Yeah, so BFS you can use here, but here you have to return the path, not just the traversing. So you have to return the path from start vertex to end vertex. So suppose,
So the end vertex is 7 or 5,
no, I'm just giving example 5 here.
but in the question it is 7, is it?
No, question, this is there are multiple test case. So
No,
here,
here it is.
yeah, for this sample question, yeah, start is given 8 and end is given 7. So 8 to 7 you have to return the path, shortest path. Okay.
Okay.
So if I take 8 and 7, okay, let me just open this graph again. So okay, 8 8 and 7. Okay, now 8 vertex is this one. This is the start vertex, and this is the destination, or we can say the end vertex. So this is S and this is end. Now you have to return the path from S to end, S to E. Okay, and shortest path. So there are multiple paths possible in this graph from 8 to 7, but you have to return the shortest path. Okay, and you have to return the list like this. If 8 is the first node and 7 will be the last node. Okay, and in between where you are going from this 8, you have to figure out this by some algorithm. So now solution is given in the problem 89913. Okay, so that means you can go like this: 8 9 9 to 1. Okay, 9 to 1, then 1 to 3. Okay, and 3 to 7, like this. Okay, so your output should written in this manner. So 8 9 1 3 and 7. Okay, so suppose in another case which is given in the problem statement, suppose there is one more node added in this graph, like 10. Okay, but this 10 is not connected from this first part of the graph, first component of the graph. So in this case, if we suppose give start node is 0 and end node is 10. Okay, so in this case you cannot reach from 0 to 10. So you have to return only start
0.
vertex inside the list, 0. Okay, so now this is the problem. Now just think about that, how you can use BFS, and to return the path, what update you need to do in the BFS algorithm. Yeah, so anyone want to just explain the strategy? Anyone want to explain the steps, how you will write the algorithms or write the steps for this?
Do we initiate visited and parent?
Yes, sir.
Okay. Visited and parent to writing for the BFS code you are talking about?
Yeah, will that be the first step?
Use BFS and reachability we can use.
Okay.
If it is present, we will give. If it's not present, we will return the start value.
Yeah. So, but if present, so you have to return the path. So, how you will find out the path? So, BFS basic algorithm is actually just return the connectivity if node is reachable or not from the any source vertex. But what update you need to do in the BFS algorithm so you can find out the path also, shortest path.
Means along with that, we should do you find the path on that.
So to find the path, what information you need to store?
Information.
Sorry?
Parent information.
Parent information, yes, correct. Yeah, Rosa.
Sir, how to calculate this shortest path from the graph?
Yeah, so shortest path here we are asking in terms of minimum number of nodes in between. Okay, so that things is actually if you use BFS, so BFS traverse the elements label wise, adjacent wise. Correct?
Yes, sir.
Okay, so in that way, if you traverse the graph in label wise, that means adjacent node wise, so definitely one BFS tree will be created, and where the connectivity of the tree from any node to any other node will be the shortest. So you can use the BFS algorithm, but you have to also store the parent information during the this BFS process. Once you get the parent information, you can return the path by traversing the reverse manner and to start.
Okay, sir.
Okay.
Sir, actually, I have created a BFS tree, but there I am saying that I'm getting more than 5 shortest paths. So maybe I'm doing something wrong.
So how in tree? Okay, in tree there is only one path possible from any node to any other node. You cannot find out the more than one path. So that tree terms is not discussed in detail, but that BFS tree and BFS tree little bit discussed in lecture also. So actually in tree, so tree means no cycle.
Yes, sir.
Okay. Now you cannot find out the more than one path from one node to another node.
Sir, anywhere you are writing?
No, I'm not writing. Okay, let just tell me here. So suppose I'm creating one sample tree. Okay, like this. Or this is the general tree. So more than 2 nodes are also possible like this.
Sir, above given graph also we can make tree for that.
Yes. So when you use the BFS algorithm, so it will generate a tree like this. Okay. Of the traversal tree, we generally see that traversal tree. So in this type of tree, you will always find only one path from any node to any other node. So suppose if you are traversing from this top node, you can see only one path is possible to any node.
Yes, sir.
Okay, and that path will be the shortest path.
So it's not clear to me, so sorry.
Okay. So in terms of this graph, okay. One second. So what source node is given? 8, correct? And
yes, sir.
what destination node is given? 7. correct? So we will apply the BFS algorithm on this 8th node. This
Okay.
is the source node. Now in the BFS algorithm, first 8 node will be traversed. Now we will check what are the adjacent nodes of this 8. So what are the
Okay.
adjacent of this 8?
9.
0 and 9.
0 and 9. Okay, so this is 0 and this is 9. So that means this 2 node will be traversed in the second level. Okay.
Yes, sir.
After that, we will check what are the adjacent of 0.
Nothing.
Yes, correct, nothing. Okay, so we will always check which what are the adjacent which are not visited yet. So here there is one
Okay.
adjacent of 0 which is 8, but it is already visited.
Yes, sir.
Okay, previously. Now this no, correct. Now what is the adjacent of 9?
1, only 1.
Okay, so there is one outgoing edge, correct. So here we will make 1. Okay.
Yes,
Okay,
sir.
so now from 1, just tell me what are the adjacent of 1 which are not visited. Visited means which are not exist in the current tree.
5.
3 and 5. 3
So,
and 5.
Yeah, from 1, so 5 and 3. Yes, 3 is also there. Yeah, correct. So 3 and 5. Correct.
Yes, sir.
Now,
Yes.
what are the adjacent of 3?
7.
So
7 and
adjacent
2.
of 3, 7 and 2, and 2 is also not visited. Okay, so I'm writing 2 and 7. Okay, and what are the adjacent of this 5?
4.
4, only 4. Okay, so 4. Okay, now what are the adjacent of 2? Any node is remaining for 2? Yeah, 9. 9 is already visited.
Already visited.
So no node is available which are not visited from 2.
Yes,
Now
sir.
from 7. Okay, let me
Uh,
check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so one node is also remaining. Which one? Oh,
6 is
Six.
6 is remained.
okay, 6.
4.
Let me
From
let me
4.
check from 7. 7, there is no node. Now from 4, yes, 6.
6.
6.
Okay. So now this traversal order will be generated. Traversal tree will be generated by BFS. So this is the BFS algorithm working. Okay. We are
Okay.
traversing the node from adjacent wide. So first this one, second is this one, third level is this one, fourth, and then fifth, then sixth. Okay. Now if you see the path, so 8 to
Yes.
7, what is the path? 8, 9, 1, 3, 7.
Yes, sir.
Only one path will be possible in this tree from any node to any other node.
Okay.
Okay,
So
so
number
this-
of nodes will be the answer.
No, you have to return the path sequence. What are the nodes sequence in the path?
Sir, will there be a difference if we take it on EFS?
Yeah, DFS, the
What we
strategy
have
is
done in
different.
DFS, no?
Yeah, BFS. So in this
If we
problem,
take it on DFS, what will happen?
so the different traversal tree will be generated, but basically to find out the shortest path. So this is the best suitable algorithm for this BFS.
Sir, we have to return the path or the number of nodes?
Path.
Because in the output it's shown 5 is the solution.
No, I think there's one list in the output. Sample return. You have to return the list.
Okay.
Okay, you have to return the list and output.
The 5 is the level, no? Number, the level.
Yeah,
It is
number
going
of-
up to
number of
level
nodes.
5.
I think
No,
the suffix code is printing the length of the.
Yes, correct. So your function should return this list, and suffix code is actually calculating the length of this list.
So, sir, that list is the nodes, no?
Yeah, in nodes in path. Number of
Okay.
nodes in path.
Hello, sir.
Yes.
Means we are using DFS or
No, BFS, breadth first search.
yes, that I heard DFS, so I got confused.
No, BFS. Okay, so got it. So you can see here path is coming. This path is shortest. If you apply the DFS, so you may get the longest. You will not get the shortest path by the DFS. Okay, so suppose I've applied the DFS algorithm from 8. So what will be the traversing? What may be the traversing? So 8 will be the first node. Okay. After that, what are the adjacent of this 8, 0, and 9? Okay, so if you move to the 0, then you will check again what are the next adjacent of this 0. But here there is no adjacent of 0. You will reverse back to the 8. Then you will check the second child of this, second adjacent of this. Okay, so that is 9. So once you reach to the 9, you will check the adjacent of 9. So adjacent of 9 is only 1 here. So you will get only 1. Okay. Now what are the adjacent of 1 this time? So adjacent of 1 is 3 and 5. So you will move to 3. Now you will check the adjacent from 3. Okay. What are the adjacent of 3? Adjacent of 3 is 7 and 2. So you will select any one adjacent, like you are selecting 2. Now you will check what are the adjacent of 2. So adjacent of 2 is 9 and 8. But 8 is already traversed, 9 is also traversed. Okay, so we will not check again. Now we will reverse back to 3 and we will check what are the adjacent of 3. So 3 adjacent is 7. Okay, so we will move to the 7 and we will check what are the adjacent from 7. So okay, 8 is already traversed. Now we will reverse back.
Sir, why do we need to continue that one when we need one?
No, depth first search means first we will complete the depth where we can reach. So what are the end point of the depth we can reach? We will complete the depth, then we will reverse back if
Sir, why do we need to continue this one when we are asked find from 8 to 7? Once we mapped from 8 to 7, then the problem is over. No?
Yeah, but you have to perform some process, na?
Why? Where is it given in the question?
Okay, so you can also just apply some break. If you are finding the path, you can apply the break. Okay, so there is no restriction for that. But if we are solving any problem by any specific algorithm, we have to perform that algorithm completely. Then we will find out the this parent information, then path information, then we will return the path.
Completely. Okay, so that is the way we should always approach it.
Yes. Okay. So if you can apply any break condition, you think that you have already find out the complete path which is required for the question, you can just break, and if you have already done the sufficient information, okay, then you can stop your process, then you can return back the answer. So you can update your solution code.
So through DFS also we can get only one path.
No, yeah, path you will get the one, but path may be different. So that path will not be the shortest path. So maybe for some example, maybe for some example, you are getting the same path. So let me complete this by the DFS. Okay, so 3
but
to 7.
But if there is any question which is asking for multiple paths, finding all the multiple paths, then we will apply DFS.
Yes, you can apply the DFS.
But you're saying that
one thing, if we are asking just path, okay, then we can apply DFS also. But here we are asking the shortest path.
Yeah,
so DFS actually guaranteed that path will be the shortest, because we are traversing the node label wise. Here we are not traversing the node label wise. Here we are traversing depth wise.
Yes, sir. Okay. But my question is not that. My question is that if we want to find all the paths,
you can apply the DFS also. So in the next maybe next problem, this is the question. Actually, we are finding out the different unique path from any node to any other node. So we will discuss that also. Okay. So, but here, for example, if I update little bit this problem, so let me just update some modify. I will do some update. So 1, 2, 2, 2, like. Okay, 2, 2. This next one is the 5 to 4. Okay, so let me connect this vertex. Okay, 2 to 5 in the original graph. So what will happen actually when we traverse this 2? After that, so before going to this 7, so if we are traversing 1, then 1, 2, 3. Okay, then what are the adjacent of 3? This is there is one 2. Okay, then 2 adjacent is 5. Then path will become like this. So 2, 5. Then what is the adjacent of 5 is 4. So all nodes will be connected in that way, like this. So this will be the traversal if we connect this 2, 3. But BFS, you will get the same order. So after 1, so what are the adjacent of 1 is like this is the 3. So yeah, 3 and 5. So 3 and 5. So we will check the what are the adjacent, all the adjacent of 3. So adjacent of 3 is this 2 and this 7. Okay, so we will mark this. So we are traversing the nodes adjacent wise. We will complete the traversing of all the adjacent first, then we will move to the next level. Okay, but here in the DFS, we will complete depth first. We are not completing the all adjacent level. Okay, we will complete, we will just select the one adjacent, then we will check the another next adjacent of that node. In that way, we will complete the depth first.
So would you mind in writing BFS and DFS on the top of each?
So this is BFS.
No, this is the BFS. Okay.
Okay, and here this is DFS of this. Okay, I have just modified little bit this to make the difference in between the traversing. Okay, 2 to 5, I have added one new edges. Okay, if I added this, you can see DFS we are getting like this.
So, sir, in the suffix code, we have to write the whole queue and the BFS and then this algorithm, the full.
So 1 second. Yeah, you have to write the BFS code algorithm for this.
Okay.
For this problem main code. So only this suffix part is given. You have to write the required function. Okay, so what things is required to write the solution, you have to write. Okay, so this is one application of the BFS. So you can find out the shortest path in minimum number of hopes and minimum number of edge in the path in terms. Okay, here weights are not given on the edge. Okay, so we are finding out the shortest path in terms of minimum number of edge or minimum number of hopes in between the source and vertex. Okay, so you can apply the BFS algorithms.
Sir, can we discuss code?
Yeah. So, anyone have written the code?
Yes, sir.
Okay, 1 second. Okay, so I'll try. I am also writing the code here. So what things which we just did with this graph? Okay, so this adjacent node wise, we are traversing each node level wise. So just think this like as a problem and just write the code according to that. So no need to remember the BFS code. Just remember the approach of BFS. Okay, remember the approach of BFS and just try to write your code for the BFS. If you will try to learn the code of all the algorithms, you cannot recall the code. Okay, so if you know we just traverse all the nodes label wise, adjacent wise from the source, then you can write the your code also. So like BEF, what function we have to write? This
BFS.
Minimum hope. Okay.
Yeah.
So see the main function we have to write. Okay, and what things are given in the, okay, so this a list. A list comma start comma end. Okay, so this is the main function where we have to return the path. But after getting some information, so BFS algorithm, if you know that, if BFS algorithm we can use to return the parent information and visited node information, if node is visited or not, this type of information we can return by the BFS algorithm. So we can call that algorithms after getting the parent information and visited information, we can find out the path by different code. So first thing, you can write the code for BFS algorithm, where you can maintain all this parent information in some data structure. So like we can write BFS, and we will pass the same thing. So this a list. So a list is okay. I will take the same name. A list, comma. And we need to just pass the start source vertex. Okay, so start. And this algorithm will return the label and parent information for each node which we are traversing. Okay, so Replit AI is actually giving some suggestion for the complete code. Okay, let's remove. So this is the feature of Replit AI. If you write something, they will directly provide the code. Okay, so what information we need to store? We want to store the label or visited information, okay, and parent information we need to store. So suppose you can write the visited and parent equal to, you can create two dictionary, and initially you have to you can initialize this dictionary with some value. So initially all vertex are not visited and all parents information we don't have. So we can initialize some value for this. So like we will traverse each vertex from the A list. So for V in A list. Okay, so we have the vertex information A list dot key. I'm traversing all the vertex node, okay, from the adjacency list, and I'll just make this visited of V equal to false, and parent of none we can also store as in none. So this is the two things we can initialize. It is writing something, anything. Okay, so V in A list dot key, we are traversing each node, then we are initially set all the vertex are visited false, and parent of V equal to none. Okay, after that, so this is the one loop for the initialization. Now we will start from the start node. So we have to set the visited of V. Okay, and visited of V to true for this.
Sir. Sir.
Yes.
Hello.
Yeah.
Sir, I can't get this. Why you are putting this visited as false and parents as none?
Yeah. So as I explained in the example, when we are traversing, okay. So suppose we are starting from this 8 as a source. Okay. Now when we are traversing adjacent wise, so first we will always check the adjacent of this current node. Okay. So now 8 adjacent is 0 and 9. So once we will traverse this 0 and 9, we will not traverse again this node. So because of that, we are marking that this node is traversed. And every time when we are checking, so what are the adjacent of the current node? If maybe, so you will get the 0 for is the adjacent of any another node. So but we have already traversed 0, so there is no need to visit again that node. Okay, so that we can identify that by this visited dictionary. If this is marked as a true, then we will not check again. We will always check the adjacent which are not visited. So that, well, if the value of node is false, then we will identify that this node is not visited, and then we will consider that for the visit. Okay, because of that, we are just maintaining this one visited dictionary. Parent, we will always contain the node as a parent where from we are coming. Okay, so what are the parent node of any node? Parent node means if we are coming for this, so 8 from 8. Okay, so this is the first node. We can traverse 8 to 0 and 8 to 9. Okay, that means on 0 where from we are coming 8, and on 8 where from we are coming, so for 9 8. Okay, so this 8 will become parent of 0 and 9 both. Okay, so parent of 0 is 8, parent of 9 is 8, because we are coming from this node by direct edge. Okay, so that information we will store in the parent dictionary. So initially all are none. Okay, so now this is the first thing, visited v equal to true.
So visited should we start? Visited start should be
that start, correct. So this is the first step. Now for BFS, and we generally use the Q data structure. Okay, Q data structure, and for DFS we use the stack data structure. So we will use the Q, and you can there's no need to implement the Q completely here. You can also make the list and just perform the operation in that way, similar to Q. So just add the element in the last and remove the element from the first in the list. Okay, so you can directly use the list as a queue. So no need to write the separate code for that. So you can make a list as a queue and insert first start node in the queue, because we have already marked that visited start equal to true. This node is visited. So just write this q dot append. This is start. Okay, so this is the initial things which we are setting. Now here,
excuse me, sir. Sir, on line 4, is it supposed to be alias.key or keys?
okay, so this keys, yes, correct.
Sir, is key a method?
Yeah, this is for the dictionary. If we want to get only keys information from the dictionary, so we can use this.
Okay.
So actually we just want to read the keys representing the nodes in the graph. Okay, so we want to just read the all nodes value of the graph. So because of that, we are directly using this alias.keys. Okay, now this is the first things. From here we have to apply some things repeatedly. Okay, and so in that way we will use the loop here. So what condition we can take here? So here we have just inserted one element in the queue, and every time we will just remove one vertex from the queue, and we will insert all the unvisited adjacent of that vertex into the queue. Okay, so this process we will repeatedly use. We will repeat this process until our queue will not become empty. Okay, so now here you can just write the condition while so len of q is greater than 0.
Sir. Sir, hello.
Yes.
Sir, can you keep that graph side by side so that you are writing, and if the graph is also here, then this will be more clear. I think yes.
Okay. So this part is very less. Fine.
Yes, sir. Okay, thank you.
Okay, so what we are doing, we have just finalized this thing. So start node here, we are suppose we are giving 8 as a start. So what we have done, we have marked this node as it visited true. Okay, now what we will do, we are taking one queue and we have inserted inside 8. Okay, this is the queue. So queue definition you have already learned in the big 3. Every time we will remove one element from the front, okay, and we will insert all the element from the rear backside. So we will repeat this process until our queue will become empty. So this condition we have marked here, len of queue is greater than 0. So initially this length of queue is 1 because we have already added one first node. Now in the first step, as I mentioned, that remove that vertex from the queue. Okay. So Power Code is already come. This feature I have to close, I think.
So you can turn off the AI suggestions from, just click on this AI, just line below 12, you see AI, you can click on that and yeah.
Thanks. This feature is just added. Okay, so now the first step is J. We will just read the value. We will remove the one node from the queue and just read that. So J equal to, suppose we are taking J equal to, and how we will read? We will read the first element of the queue. So to read in that way, you can write like this: queue dot pop is the first element. So pass the 0 index. Okay, so here this element will be removed from the list. We are using pop here and passing the 0 index. So first element will be removed from the. Okay. Okay. So after that, we can mark this as a visited. We have already marked. Okay, for the first node. Okay, so that is fine. Okay, so this is the first thing. After that, we will just check the all adjacent of this J. Okay, we have removed the element. We will check all the all adjacent of this J. So for like K in. So where from we can find out the adjacent? We can find out the adjacent from adjacency list, where the value of key contains the all adjacent. So we can directly pass this a list and pass this J. Okay, so this will return all the adjacent of this J, and we will read all the node in K one by one. And after that, what we will do, we will just mark as a node, this node as a visited, and we will also contain the information of parent node. And also we will note down one more thing. So if K, okay, one more condition. If this K visited of K, so visited of K not equal to true. Okay, so adjacent which are not visited, then we will just consider that adjacent. So what we will do, we will just mark visited of this. Is okay or not? Yeah. Okay, equal to 2. I think this visited equal to 2. Now we will also store the parent information here. So what is the parent of this K? We are reading all the adjacent, and so adjacent of so these all adjacent are for the J. So that means we are reading all the adjacent of J right now. So parent will become J. So here parent of J, parent of K will become J. So this is the first thing, and after that we will append this.
Can you clarify this, the line 13 and 14? if visited of k is not equal to true, then visited of k is true. What is the logic?
Yes. Yeah, so we are traversing the node adjacent wise. Okay, so suppose if we have read this 8, we will remove this 8 from the queue and we will check what are the adjacent of this 8. So 8 adjacent are 0 and 9. Now we will read this 0 and we will check this is already visited or not. Okay, if this is already visited previously, so we will not consider again. If this is not visited, okay, if this is not visited, then we will visit this node and we'll mark this as it visited is equal to true, and we will make the parent of 0 is 8. Okay, in this manner we are doing. Then we will read the second adjacent. So this is 9. We will check this is already visited or not. Then if it's not visited, then we will mark as a visited, and we will make the parent of 9 is 8. Okay, and we will also insert all these adjacent into the queue.
Okay.
Okay.
Got it. Thanks, sir.
Yes. So after that, we will write this q dot append of this k. Okay. So now this become our BFS code, and after this BFS code, we will return both information. So return. You can return this visited comma parent. Okay. So this is the BFS code. And after that, so here parent information we are getting. So inside the minimum hops, what you can do, you can call this function and you can make some variable here. So like p or not p, vis comma par.
So we have to DQ also one, na? The visited start one.
Sorry, which one?
So from the BFS algorithm, we have to DQ the visited.
No, I have not written the separate code for this queue. I am just using the list as a queue.
Yeah, but
so here you can see that for in queue, in DQ means we are removing that first element. So we are performing this operation by this q dot pop 0.
Yes. So when we like we are done with the J, like from line number 12, we are done with the J.
Yes, we have removed one node from the queue, correct?
Then we have to remove J.
So remove this operation is already removing from the queue.
Okay, it's removing the J.
Yeah, this pop is actually will remove.
Okay, it's removing the before starting the loop.
Okay, so the one first index element will remove, and will the value will be come at the J. Okay.
Yes.
And after that we are appending all the adjacent of this J. Okay, so now we will call this function
anywhere, no? We have not used DQ anywhere, no?
DQ and sorry.
A pop is the both same.
Yeah, DQ and this in queue is the operation of queue. If we are using the queue inbuilt queue, then we have to write this method. But here what we are doing, we are just creating one list, and we are using this list as a queue. Okay, so what are the operation of the queue? Enqueue and dequeue. Enqueue means we add one element. No, enqueue means we add new element into the rear and the back side. Okay, dequeue means we remove the element from the front.
Yeah.
Okay, so these two operations we are directly performing with the list. You can see that. So here we are performing.
But we are not used it in the code, is it?
So in this code we are not using. You can also write the separate class for that, and you can call. Okay.
Oh, okay.
So to save the time, you can directly use list as a queue or a stack.
Without class, we cannot use enqueue and dequeue.
Yeah, you cannot use. Yeah, you can just include. Import some library for that dequeue library like this, and directly call this function. Okay, some library is available in the Python for the queue.
So directly you cannot use NQ and DQ.
No, you cannot use directly. If this is not defined in your code, you cannot use. Okay. So here, this is the information we have received.
Hello, sir. Hello.
Yes.
Hello, sir.
Yes.
So, which is the library that implements Q?
Actually, I also not used this library directly in the code. So I think some name anyone have used.
Is it NumPy, sir?
No, not NumPy. NumPy is not. There's some separate libraries there. You can just search on the Google what library is used for the queue. Okay.
Okay, so thanks.
So yeah, don't try to use this library in the initial of the course. Okay, because we are learning these implementation. If you use this library direct, first try to implement all the things by your own, but after that just try to use this library directly.
So just ask.
Yeah, no problem. Yeah. So okay, so this is the part things. After getting the parent information, now we can just write the code for the path. So here we have to find out the path. So we can write like this path. Initially, we can make empty list. Okay. And after that, we can check the condition in the visited. Okay. If so, what is the end vertex is end. So we will okay. So how to find out the path? Just explain this thing. Okay. So for this 8 to 7, so what information we will get? So for 9 actually, so 8 is the first node. So there is no parent. So none value should be stored in this 8 parent. Okay. But for 9, parent will be 8. Okay. And for 1, parent will be 9. And for 3, parent will become 1. And for 7, parent will become this 3. So this information will be stored. If you see the graph which I have just mentioned in the previous, you can see this. Okay, so parent of 7 is 3, parent of 3 is 1, and parent of 1 is 9, and parent of 9 is 8. Okay, and there is no parent for 8. So this information will be stored in our parent dictionary. After that, what you can do, how you can find out the path now. Okay, so you can start from the end node. First thing, according to the question, you can check this node is visited or not from 8. So if this node is not visited, directly return first node as a answer. So this is the one case which is given in the problem if destination node is not reachable. Okay, so we can just check this condition if end and VIS, so VIS and equal to if this value is false. So we can return a list which contains only start. Correct? Else, if this is not true, then we will write the code. So how we can recover the path here from here? So we have the parent information. So we will start from the end node. Okay, so end node is 7. Now we will read the parent node of the this end node. What is the parent node of the parent dictionary of the 7 is 3. So we will get this 3. Now we will repeat the same process. We will check what is the parent of 3. This is 1. Now what is the parent of 1, which is 9. What is the parent of 9? This is 8. Okay, so we will repeat this process from end to start till when we are reaching at the start node. Okay, so we will repeat this process. So we will use one while loop here. Okay, while okay, so what definition we can take? Okay, so every time we are appending the okay, so end to the end. while. Okay, so we will add this path into the list. So path minus 1. Last element is not equal to the start. Okay. So we are appending all the parent information in the list, if this path. Okay, and if last, so we will repeat this process until our last element is not equal to the start node. So you can see if you are starting this process from the end, so we will add this information in the list like this: 7, 3, 1, 9, 8. Okay, in repetition we will check what is the last element. So suppose initially we have only 7, so this is the 7. This is not equal to our start node. Okay, then we will add 7, then 3. Then we will check this 3 is not equal to start node. Then we will add 1. This 1 is not equal to start node, like this. Okay, so in that way we will repeat this process. So we will just check that new node. So like this and we can take any variable here. Path start and equal to. Okay, so where is the PAR? So PAR of 1 second. We have to take. Okay, start. And shortest part. Okay, yeah. So what we are doing, initially we are starting from this end, correct? So end is the last node. We will read. So
but we need to append this into path, no?
Sir, can you explain from the while, sir? Once again.
1 second. I am just writing the correct code.
Path dot append the start node. No, the end node.
And okay, so path is the parent of the end. Parent of end.
So path dot append the end node.
And 1 second, parent of end. Okay. So what we can do, we can just append one node in the end like this, and we can write like this end. After that, what we are doing, we are just checking if last element is not the start element. What we will do, we will just read the parent of this current end node. Okay, what is the current end node is initial first. Okay, and okay, so for the confusion we can take any other value. Repeat this. We can set like this: node d equal to end. So initially we have set it node equal to end node. Okay, so what is the last node? What we are doing, we have already added this node into our first node as a path. After that, what we are doing, we are simply checking what are the parent of this current node nd. So what is the parent of this? So in this example, we are starting from the 7. So this is the end node 7. So first we have already added in the list 7. Okay, now what we are doing, we are checking what is the parent of this 7. So parent of 7 is 3. Okay, so 3 will be stored into the nd, and that we will add into our this path. So like path dot append nd. Okay, so now this process will repeat again and again. At any in last, we will reach to the start node, and that at that time this while loop will terminate. So you can just assume that we have added in line number 25, we have added 7. Okay, so this is the 7 is the last node. After that, what we are doing, we are just checking what is the parent of 7, 3. Now 3 we will add. Okay, and every time we will also check what last node is equal to start node or not in the while condition. And then we will repeat what is the parent of 3, 1. So we will add 1. So 7, 3, then 1 in this path list. Okay, Now what is the parent of 1? Is 9. Then parent of 9 is 8. So at that time, 8 is now equal to the start node. So at the time, this while loop will terminate. So you are getting a list like this, 7 in this manner. But we have to return the path from start to end. So now we are getting path from end to start, but we can just reverse this list. So just do this one operation. You can return the reverse of this list. Return of this path like this. Not here. Yeah, correct here. Yeah. So this is the.
So can you please repeat this part again? I did not get it.
So what we are doing, so we are getting some one parent dictionary, okay, that contain the parent node of after DFS traversal. Okay, in this parent traversal, suppose we are getting, so like this is a dictionary which I just mentioned. You will get this type of dictionary. So parent of 8 is none, parent of 9 is 8, like this. Okay, so in this manner we are just receiving, and VIS, so this VIS we are just receiving visited dictionary, which contain the information node is visited from 8 or not. Okay, when we are starting BFS, the node, all nodes are visited or not. This true and false for all nodes. So these two dictionary we are getting from BFS function. After that, we are just finding out the path. So path information, we have parent information of each node. So you can just apply the reverse logic from end to start. So just you can find, so what is the end node? Okay, so that end node, first condition in line number 22, what we are doing, we are checking that end node is traversed or not by the BFS. If end node value, visited value equal to false, so that means this end vertex is not connected from the source vertex. So this is the separate component like this. Okay, so this is not reachable from the vertex. In that case, you will get the end visited end equal to false. So you can directly check this condition in 22 line. If visited of end equal to false, in that case, directly return a list which contain only start vertex. So start vertex is 8. So we are just returning start vertex list. Else part. So in the else part, first we are taking one list path. This is initially this is empty. Now we are just storing the end node. Okay, so our start node is given. For this example is 8. So this is start, and end is given 7, like. Okay, so what we will this code is actually first adding the end node. So what is the end node is 7 in the path list. After that, we are just taking one we are using one loop. We will just calculate the parent of the current node, and we will add the parent information in this path list. Okay, we will repeat this process till when we reach the start node. Okay, so we are just starting from the end node 7. So we have already added this. Now we are just checking what is the last node of this path in line number 27. So path -1 is representing the last node of the list. This is equal to start or not?
Excuse me, sir. Sir, can a node not have more than one parent?
No. In tree, it cannot have the more than one parent. So in DFSL traversal, if any node is visited one time, we not consider again, na? So that parent information cannot be more than one. Okay, so this example, if we have traversed 0 one time, okay, so we have already stored the parent of 0 is 8. Again, if we are reaching to the 0, so if 0 is already traversed in our process, we will not consider that. So we will not update the parent information for this. So parent will always be stored one node.
But in the graph, it could actually have more than one parent, right?
Yeah, more than one parent. But here we are finding out the shortest path. So BFS traversal is actually generate one tree, and in tree, always you will get only one parent.
Okay, sir.
For the shortest path. So in this manner, we are doing this.
Reverse is true, is it?
So why
more than one child will have same parent, no? But that does not affect the path.
Path information. So you may get a different path if you look the graph, but this BFS algorithm will return only one path, and that path will be the shortest path.
So why have we created a new parent dictionary? Can't we use the one that we have created with the BFS?
No, that actually we are calling this function from this main function, minimum hopes. Okay. After that, what BFS function is returning, we have to store some place now. So we are just created two variables.
So if we just return the BFS function without means if we don't store it, then it will return visited and parent, and then can we not use parent that way? Means I'm just asking because I don't know that.
What
like if we don't assign this variables.
But this actually visited and parent is the local parameter, local variable for only BFS function.
Okay.
Okay, so that function cannot be accessed from this second function if these are not global.
And that is the reason we have defined it here.
So here actually the first function is returning some things. So two dictionary we are returning by the BFS, and that dictionary we have to store some place. So two value we are returning from BFS. So that two value are stored in this BIS.
And if we don't do this, this won't be called.
You cannot call this visited and parent if these are not global. Okay. So in this manner, you can find out
You don't need to define parent before we using it. Like line number 20, first time you're using it, no?
20, yes.
Parent.
What you are asking?
We don't need to define that one before we using the parent.
No. Python there's no need to define. This function is actually returning to dictionary. We will directly read that. So this first return value from the function will store inside this VIS. Okay, second return data will be stored in this PAR. Now we can directly use the data with the name of VIS and PAR.
Okay.
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 Yeah.
That is value or dictionary, sir?
Sorry?
This visited and parents are dictionary or value?
Dictionary. You can see in the BFS function we have created dictionary. Okay, and these two are dictionary, and we can directly read the value in our code. Okay, so I hope approach is clear.
Yes, sir.
So this parent information things are important. This will again come in the big 5 also, so where we will just use the shortest path algorithm. At that time, you have also find out the path. So this parent things is important. So just note down these things. How you can, if you have parent information of each node, how you can find out the path. So you can start from the destination and just check what is the parent of destination. Then check what is the parent of the destination parent in the reverse way, and you will repeat this process when you are reaching the start source vertex. Okay. So this is the thing.
Share the code, sir, in any.
Okay. So you can see 1 second.
Create one link on the share.
So I think if you have got the logic, you should write the code. We will share the solution of this.
We understand the logic, but
so just try to write the code. You're okay. Don't read the code. So this is the BFS which you have already learned in the course. So same BFS algorithm I have just written. Okay. And after that, we are getting this visited and parent information, and this is the main part of this to return the path.
Can you copy and chat back, sir?
Okay, so BFS code you can directly use from the course. That part I am just sending you. Okay, so now this is the first problem. Now move to the second. So okay, so let me open the second problem. Three, four. Okay, so let me explain this second problem, and you can also help me to understanding. Write a function back and forth. Okay, so this is also a where the adjacency list is given for the graph, and two vertices are given n1 and n2. Okay, here write a function back and forth with this information to return the maximum number of possible route. Okay, maximum number of possible route between node n1 and node n2.
Sorry, sir. Sorry to interrupt.
Yes.
Sir, that test case 2 is it's failing.
So which code you what's your name?
Siddhant, sir. Siddhant.
Let me check your code.
I written the same code. I typed the same code. But...
Okay, just check. So yeah, now you can debug the code. So maybe someplace. Okay, so some only one case is failed, na? Okay.
Yes, sir. That is failing.
So this one. So some error is coming. Object of type int has no length. Line number 40. Oh, you are not returning. Okay, so you have to return list here, not start only.
Okay, sir. Okay, sir.
Correct? Yeah, passed.
Yes, sir. Yes, sir. That was my mistake, sir.
Okay, so second problem. Yeah, write a function back and forth a list n1 n2 to return the maximum number of possible route between node n1 and node n2 in the undirected graph without going through the same node again, with exception to n1 and n2. The connectivity details between nodes are provided by the adjacency list a list. Okay, so here also one adjacency list is given. So let me just explain this problem with the example. So what is asking? So this graph is suppose given. And source and destination, and one is 0 and 2 is 1. So and 1 is 0 and 2 is 1. Okay, so these two nodes are given. You have to return all possible path from 0 to 1, which connect 0 to 1. Okay, but you cannot repeat the same nodes in between which you have already used in one path. Okay, so let me just find out some path in this graph. So 0 to 1. So what are the possible paths for 0 to 1? So I'm just writing some one path. So 0 to 1, you can reach 0 to 3 and 3 to 1, correct? Okay. So like 0 to 3 and 3 to 1. So if we have used this 3 in one path, okay, so we will not consider this start and last node 0 and 1, but those nodes are coming in the path. We will not repeat that node again in the another path. So if we have marked this node, this path one time, okay, this is considered. Now then we will not use this 3 in any path from 0. So what another path is possible in this graph without using this 3?
Sir, if it's coming from, like, in example, if it's the same as 0, 3, 6, 1, then also we cannot use 3.
Huh.
Okay.
So I'm just taking one example. So if I consider this path as a first path, okay, then I cannot use this 3 again in any other path, because we have already considered this 3 in one path. Now second path, what I can just choose. So suppose I'm taking 0 to 6 and 6 to 1. So 0 to 6 and 6 to 1. So this is the another possible path like this. Okay. Now here we have two paths. Okay, so 0, 3, 1, 0, 6, 1. Now I cannot use 6 in the remaining possibility. So what are the other path possible?
If you can take 0, 3, 4, 5, 1.
No, 3 we cannot use, no, because we have already used
that
this.
was my question. Like 0,
No,
3, 4, 5, 1 we cannot use.
No.
Okay.
So we cannot use now 3 and 6 in any path. Okay. Now what another path we can use, like, so 0 to 2. Okay. And 2 to 4. And 4 to 5. And then 5 to 1. Yeah. So if I consider this path, now you can see that no other path is possible. So because this is considered like this, so 0. Okay. So now all the nodes are traversed. You can see that 3 is considered 6, 2, 4, 5. So now no remaining paths are available. So how many paths are possible if we are just finding out this in this way? 3 total. Okay.
Hello, sir.
Yes.
So can you just explain that? I'm confused still.
This problem?
Yes, sir. Yes, sir.
You are asking the explanation for this?
Yes, sir. This problem explanation.
Okay. So as I mentioned, one input graph is given. Okay. Let me remove everything again. Okay. So here, and 1 is 0 and 2 equal to 1. This input is given. One graph is given, and graph is given in the adjacency list form. So a list, one adjacency list is given, and this is the logical representation of graph. Two vertices are given, and 1 equal to 0 and 2 equal to 1. So this is the and 1, okay, and 1, and this is the and 2. Okay, now you have to find out the path from this end 1 to end 2, and how many paths are possible from this 0 to 1, but you cannot use any vertex twice in two paths. Okay, except this initial and last node. So you have to calculate total number of paths from 0 to 1 without repeating the intermediate nodes.
Only start and end must be same, except in middle,
yes.
Nothing.
Yes, correct. Okay, so how many total number of possible nodes are there? So in this case, I am just taking example. If I consider this 0, 3, 1. So first I am taking this 0, 3, 1. So I cannot use 3 in any other remaining path. Okay, so this is one path. Second possible path.
Can I interrupt you there?
Yes.
Because in the question, except 3 and 1, except 0 and 3 is given, no? So you can use it more than one time.
No. Sorry. Which sample you are giving?
Now the problem 2.
Huh?
Can you please go back and what is the exception given here?
The exception is given like this. Yeah, in the graph without going through the same node again.
Exception to end 1 and end 2. No, so there you can do.
So this end 1 and
more
end
than
2,
one time.
these two nodes definitely will come in each path. So these are the source and destination. But
Yeah, that is the case. Then the number of paths will be more, no?
How?
Can you please go back to the page where you have 3 nodes written?
So
Here,
this
here.
is the initial 0 and 1. We are
0,
saying
3 and 1 and 0, 6 and 1, that is.
0, 6, 1 in the another path. Third path we have mentioned.
Then
right?
you said 0, 5, 1 also, no?
So 0, not
4, 5, 1.
How you will directly reach from to 4, 0 to 4?
No, not that.
Okay. 0 to 2, 2 to 4, 4 to 5, and then 1.
Yes.
Okay. So here initial nodes definitely will be same. Last node will also be same. Okay.
Oh,
but
that exception is only for initial and
yes.
end
So
node.
that will be same actually in the path. So we are not repeating the intermediate nodes in the path.
But given path, you cannot repeat the end nodes twice in a given path. Like for example, we cannot take it 0, 3, 4, 5, 1.
0, 3, 5, 4. Sorry, 0,
3, 4, 5, 1.
Okay, so suppose if you are taking this path like, so 0 in the first path, as the first path, 0, 3, 4, 5, 1. Okay, so suppose if you choose this path in the first, and what are the second path possible now?
0, 3, 4, 5, 6 and 1.
No, 3 you cannot repeat now.
But it is given, exception is already given, no?
Intermediate nodes you cannot repeat. You cannot use the same nodes which you have already used. Exception is only for the source and destination, first and last node.
Alright, it is not that 3 and 6 is always.
No.
Okay, got it.
Okay.
Thank you. Right.
So how many paths are possible? So that information you have to calculate. So just think about the general way how you can write. You have already solved one problem where we have find out the path, one path, shortest path. Now just relate to this that previous problem to these problems. How we can approach this?
Sir, in previous problem we have find only shortest path, but here in this question we are expecting like to find all the possible paths.
Yes. So can we use the previous approach here?
Yes, sir, we should.
Yes, sir.
So one thing, you can apply the same previous approach on this graph where the start node is 0. Okay, I'm just giving one simple hint here. So start node is 0. This is start, and end node is 1. So you can apply the same previous code here, and that will return one shortest path to 0 to 1. Okay, so that will be the one path where some nodes will come in the between. So maybe you will get like shortest path 0, 3, 1. Okay, one possible path. So this is the one shortest possible path. BFS algorithm will give any one shortest path. Okay, so there is no direct. It may be 0, 3, 1. It may be 0, 6, 1. So according to the algorithm implementation, algorithm will return only one possible path, shortest path. So after getting one path, how you can use the same approach again, and what modification is required when you are using the same algorithm again?
We can add the path to the list, separate list, and the other paths we can add it to the list, and finally we can get the maximum routes possible.
We can remove the intermediary nodes, right? And do it once again.
Yeah, correct. That is also fine. Yeah, so that things you can just think about here. If you have find one path, okay. So what nodes are coming in between that path? You can just note. You can make some list, separate list where you can just collect the intermediate nodes. Okay. So suppose you collect the intermediate nodes is 3 in the first path. Now in the second time when you are performing the same process, just do not consider this node in the adjacent node. At the time of calculation of adjacent node, if that adjacent nodes is exist in this list, just ignore.
Means we can have dictionary, and if we have in that true, then we'll just not consider it.
So here you can just you can modify little bit the same previous code, BFS code. But you can just pass one more list in the function, and that contain the this intermediate nodes. In the first call, just pass the empty list. Okay, first pass the empty list, so that BFS algorithm will return one shortest path like 0, 3, and then 1. Okay, now you just store this intermediate nodes in the intermediate list. Okay, so this will contain 3. In the next time when you call this the same BFS again, and the start and end node will be the same, start node will be the same. So at that time, in the BFS code, just check this condition. If adjacent node is exist in this list, okay, intermediate node list, just ignore. If not exist, then consider. So that BFS algorithm will ignore this node during the process, and that definitely it will return the second possible path, second smallest path after ignoring this 3 node. Okay, so then after getting the second path, suppose you will get like 1, 6, and 1. Sorry, 0, 6, and 1. Okay, then store this also in this intermediate 3, 6, and then call again BFS. Okay, now this 6 will be ignored by the BFS processing because this exists in the intermediate nodes. So just mark this condition in your code when you just traverse the adjacent node. If this is adjacent node is exist in this list, ignore. Okay, in that case, BFS will ignore all the paths from this 6. Then BFS will return the remaining path. Okay, so you will repeat this process until you will get the if this 0 is not reachable, then 1. So suppose in the next path, so this 2, 4, 5, and this. Okay, so 2, 4, 5. Yeah, 2, 4, 5 will also be included in this list. But once again, when you call the same function again, at that time there is no vertex available to traverse from this 0 to 1. So BFS will return a false. So that will not reachable. 1 is not reachable from 0. Okay, so you can check the visited status. If 1 is not reachable from 0, then you can stop your process. So I hope some idea you have got this. How you can. So now what update you need to do in the BFS code? Any question? Hello, am I audible?
In OPP, this type of problem will be coming, sir.
No.
Only then we can ask questions, sir.
Yeah, so one problems will come from the graph part, either from week 4 and week 5. Okay.
That is medium level or difficulty level?
Medium level. We generally give the medium level problems in the OPP exam, not the difficult level. Medium and easy. So maybe you will get 2 easy problems and 2 medium like this. Okay, so can anyone just tell me what modification we can do in the previous code? So here some prefix is already given BFS. Okay, so BFS is already given in this problem. Oh, I think solution is given. Oh.
Sir,
can
they are
anyone
asking
confirm?
right above. Sir, they are asking to write above the.
So the function is already defined. The solution is given.
Oh, solution is already given in the problem. Okay, okay. Okay, so let me explain. I will remove this solution from here. So you can just see this code. This is the main function which we are asking to write. Okay, and there is one list we are maintaining here. Okay, so stop is list like this, which I just said that the intermediate list. Okay, and initially this is empty, and we are calling the BFS function from this the first time. So visited and parent, and we are passing this a list, and this is the start node, and this list we are also passing. Okay, this contains the intermediate node which is already included in the previous path, but initially there is no path, so we are passing the empty list. Now you can see the same BFS function we are using. Some code may be different, but the things are same. But how we are using this same this stop is list, this intermediate list in our code. So only the change is here when we just read the adjacent node. Okay, you can see the same code here. We are just removing one node from the queue, and we are just checking what are the adjacent of the that node. And after that, we are checking if node is not visited, and we have added this condition here. If node is not visited, this is the general condition which we already used in the BFS. But here we have added one new condition. If this node is not in the intermediate nodes or this stoppage list which we are using name here. So if this node, this adjacent node is not in the stoppage list, okay, then we will just traverse and we will just mark that node as a true, and we will consider that as a in our process. Okay, so you can see if any node is already come in the list, that will not consider in our process. Okay, so this is the only update in our BFS algorithm. Now you can see first time we are calling this function, it will return a parent information and visited information. After that, we are just reading the count information, how many paths are possible. Okay, we have just taken this one variable count, and while visited end. Okay, so this is the condition. This means once this visited end will become false, this loop will terminate. Okay, so that means this node is reachable from the end one. So you will get true always. If your node is reachable, that means you get one path. So this while will consider as a true. If any time this end2 is not reachable from end1, this value will terminate. Okay, so we have just incremented one count after getting the one path, and we have just added path equal to path finder. Okay, so we have created the separate function. Okay, so this is the same things which we used in the previous solution. We are just finding out the path. Okay, we are starting from the end, and we are adding the parent node of the each node for finding out the path. Okay, so this function is returning the path information. So current okay, path, and we are getting this path here, and we are adding this path in our this list. Okay, and once again we are calling the same function, and we are passing the stoppage list in this function. Okay, so in that way, this loop will learn so based on how many paths are possible without repeating the intermediate nodes. So this loop will learn, and it counter will be increased by that number, and you can return the count after that. Okay, so you can just try to write this logic. You know that about how BFS code is work. Now you have already seen the parent, how we calculate the parent. Now you have to just add these things. How you can just use the counter and repeat this, maintain this stoppage list, and do the things. Yeah, any query in this? Someone trying to ask me? Yes.
Sir, actually, previous question and this question, both questions, coding part, I didn't understand. But I will rewatch this live session. My main concern is like after week 3, level of the question, like it's getting too tough for me. So what should be the right approach to prepare? Because from these two questions, I can see that I will not be able to do these kind of question in OPP right now. So that's why I'm asking.
Yeah, so because of that, OPP will be conducted after week 10. Okay, so till now you have already, if you are solving all the problems by your own in the graded assignment, practice assignment, like this, at the time you maybe have enough practice. Okay, so then you can solve this type of problems, and the OPP problems level will be lower compared to these problems. We are considering the difficult problems in the normal assignment, but in OPP exam we will give some lower level of the problems, lower difficulty level.
What will be the syllabus for OPP?
Till week 9.
Till week 9.
So just try to solve all the problems by your own. Do not collect the solution from anyone. And okay, so and the things is actually from week 4, this code part is actually become difficult. So first thing is just try to understand all the algorithms. Without knowing the algorithms, you cannot approach any problems of this week. Okay, so just focus on the implementation part of the algorithms. So do not try to learn the code, just try to understand the steps of the algorithms, and then try to write your own code.
Sir, can you explain this code once again, sir? Because I got disconnected also, so I had to.
Okay.
Sir, I just have one request. Can you provide us like a previous year OPP question and their solution for the practice?
So one thing I just want to say that many questions we have already included in our this live coding session and this PPAs. So this question which I am just discussing now, this is also asked in the, I think, term 1 or term 2.
Okay,
today all 3 questions is asked in the, I think, first term in the OPP exam.
Sir, but you said that these kind of question will not.
Yeah, so at that time in the initial terms, actually we found that students have solved these problems very finely. But after that we are getting this things, the difficulty level is now, students are feeling high difficulty level in the PDSA. So we are just reducing the difficulty level in the OPP exam.
Okay.
Okay, so because of that, we have added previous terms OPP problems in the live coding problems. Now you have some idea of the difficult problems. So maybe in OPP you will get lower difficult level problems, then you can solve this. Okay, so just solve all the problems of the live coding and this course. You will definitely do in the OPP exam. Fine.
Okay, sir. Thank you.
Yeah, so regarding the explanation of this problem, I will explain again. So you can see that the BFS function is similar to the previous code. Okay, so this is the same code where we are maintaining the visited information, node visited, true and false, and we are also maintaining the parent information. Okay, And this is the function pathfinder. Actually, in the previous code, I have included this path code in the main
So
function.
till here it's clear, sir. In Pathfinder till Pathfinder it's clear.
Okay. So what we are doing, we are just maintaining another list. Here the name of the list is given stoppage list. And I have just explained this term as a intermediate node list. Okay. If we have find out path, okay, so like for the previous graph, if we find out the 1, 3, so first we will we will call the BFS function on this 0. We will pass this 0 as a first start node, and we will just find out what is the path for 0 to 1 by using the parent information. So we will get the parent using the parent information, we will get one path. So like 0, 3, and 1. Okay. Suppose we get this path by the first call. So what we will do, we will just add this intermediate node in our list. That stoppage list which I just mentioned in the code. Okay. So that thing 3 we will add in the stoppage list. So second time we will call again the BFS function, but
how are we adding? Means we are making it a list from 1 to.
So you can just add complete list, or you can also just add only intermediate node. Just traverse the list in the path, okay, and append the nodes in. Okay. Append all the intermediate nodes in the list.
But in this code, you are just adding only the 3.
Yeah, in this code actually, in this code actually we are adding the complete path.
Also,
1, 2, 3 also. Okay. Because we are starting from this 0 and we are reaching till end. So 0 and end definitely will consider in the code. Okay. So, or you can only add the intermediate node in this, not in this stoppage list.
But here we are adding the full list.
Yeah, full list. Yeah. Okay, but you can also modify this by adding only intermediate nodes.
Okay.
Okay, so output will be the same. So here, what we are doing, so this is the first call. Okay, we are getting one path from this call, and we are also using one counter. How many paths we have find out? Okay, so we are just maintaining this counter. Now we will repeat this process till we are getting this visited of end equal to 2. So that means
N2. What is this N2?
N2 is the input. No, this N1 and N2 are the input for the problems. So N2 means the destination.
So 0 and 3 we are taking. 0 and 1 we are taking. So
yeah, so 0 is the N1 and 1 is the N2.
Okay, so we are putting N1. Okay, 1 here.
Yeah. So we are checking the status of N2. So N2 is visited or not.
Okay.
Okay. So every time if if BFS find out the path from 0 to 1, so that means 1 is visited from 0. Okay. So you will get true for this. But so after getting some path, okay. So suppose if you get first path, then second path, then third path, then 1 is not reachable from 0. Because there is all intermediate node is already used in the previous path, then now 1 will not be reachable from the 0. So at that time you will get the visited N2 equal to false.
Yes.
Okay, so at that time this while loop will terminate. So that means no paths is no remaining no paths are
all paths have been discovered, right?
Yes.
Okay.
So because of that we are running this while loop. Every time we are just incrementing the count for the calculating the total number of paths. And we are just maintaining this stoppage list, and we are calling the BFS again and again. Okay. So
the stoppage list,
this stoppage list is added here in the BFS code.
So
at the time of adjacent node visited, when we check the adjacent node of removed node of the queue, so at that time we will also check this condition. If this K node, okay, this K node is not exist in the stoppage list, then we will process.
Okay, if there is this K node, then it won't even take the stoppage list. It won't even execute this if condition.
Yes.
If there is.
So this will be actually just ignore that node which is already visited in the previous answer. Okay, so that node will be ignored for the process. So that will not consider that node will not be considered in the graph for the path.
Okay.
Okay, so this by this condition, you will get the new path by the second call. Okay. So this is the update only. Then you can just achieve the answer.
Okay, sir. Thank you, sir.
Okay, now
Can you show from line number 1, sir? Once.
Line number 1. Yeah, this is the BFS same code which we have already seen the previous. Only the update is here.
Okay.
Okay, this list, and we are also passing third parameter. This is stoppage list at the receptor. Okay, so this code is, I think, is visible to you also in the Replit team. I will remove this after this session. Okay, so then you can just write your own code. And these problems are also released on the portal. Okay, so you can also try on the portal. So let's discuss the third problem. Number 3. Okay, here code is not there. So problem. Okay, so how many of you have already seen the algorithm or understand the algorithm of this topological sort? In week 4.
Video I have seen, sir. Lecture I have seen.
Implementation part?
Lecture, all videos are completed, sir.
Okay. So actually next problem is based on the topological sort. And if you already watched the videos, so topological sort we applied on the DAG, okay, directed acyclic graph. Okay, so and the application of DAG is basically the dependency problems, where something is dependent, some task. Suppose if we take some example like a task, so any task is dependent on any previous task. So what is the sequence of the task we need to perform? So like if we take the example of your this BS degree course, so some course are actually prerequisite of any other course. So like med for the Python, yeah. So for Python you have to complete CT first. Okay, so this type of dependency. Suppose this type of dependency is given for you. So what should be the process for the course selection? How you can select the course? So what this type of problems can dependency types of problems can be solved using this topological sort algorithms. So this problem is also a example of that problem, topological sort problem. So if I see the problem statement, a group of workers have to complete a list of tasks. Okay, those tasks have dependency within the task list, but the worker prefers some interesting task and hates to do some boring task. Okay, so this problem is also asked in the first term OPP exams. Okay, they always do the most interesting one among the available tasks to be done. Write a function pool worker, a list is given and preference list is given here. So this a list is a just representation of the graph, adjacency list representation, to return the order in which the task will be done. A list is the adjacency list with the dependency, and preference is the task sorted in preferred order. In which task in index 0 is the most preferred and index -1 is the last preferred. Okay, so I'll just give the explanation. Okay, so this is the dependency graph, or if you look this graph, this is a DAG. Okay, so DAG means there is no directed acyclic graph. And one preference is also given in the question. And what is this preference? This one. Okay, So let me explain this thing. So here, this is the sequence of task. Okay, that means in this graph you can start from 0, because 0 have no dependency. So there is no edge coming on the 0. Okay, so that means 0 have no dependency. So you can select this task as the first task. Okay, so after that, if we select 0 as the first, because there we don't have any choice. You cannot select 2, because for selecting the 2 you have to complete 0. Okay, here dependency of is given because there is one edge is coming from 0 to 2. So that means you have to complete 0 before 2. So you cannot select directly 2 in the initial. But there is no dependency for the 0. So in the first time you can select 0 as a first task, because you have only one choice, you can select this. But after that, if you complete this, so if you complete this 0, so that means this dependency will be removed. So all these edge will be removed from this graph, like this will be cut, this will be cut, and this will be cut. Okay, so once you remove this edge after completing 0, how many choice you have to do? Okay, so you can see after removing this 3 edge from 0, so now 2 node have there's no incoming edge on the 2. That means no dependency on 2, but 3 still have dependency on 2. So there's one edge is coming from 2. Similar for 1. So after removing this edge from 0 to 1, still there is one edge is coming from 3. So that means to complete this 1, you have to complete first 3. So after selecting this 0 task, we have only one choice. We can select only 2. So that means second task is possible only 2. So when we have no choice, we have only one choice, we will definitely select that one. Okay, so same things we will repeat again. Now when we select this 2, now this dependency will be removed. Okay, so we have completed 2. Now this part will be removed. Okay, so this edge will be removed, this edge will be removed. Now you can see that both edges removed from 3. So there is no incoming edge on 3. So we can select this 3. And if you see this 5, but after removing this edge, still 2 edges are already coming on 5. So we cannot do this. Okay, so now we have again one choice here. We can select only 3. Okay, then we will select 3. But when we select 3, so now this 3 dependency will be removed. 3 edge will be removed. Okay, so this will be cut, this will be cut. Now you can see that 8 is now there's no incoming edge. 4 is also no incoming edge, and 1 is also so 1 have incoming edge from 5. Okay, so now you have two choice from 3, this 4 and 8. 4 and 8. Now which task you will select? So when you have more than one choice, then you will check this preference list. Which node is coming first, 4 or 8? So in this sequence, this 8 is coming before 4. Okay, so 8 is coming at the first this index, and 4 is coming after that. So that means higher preference is for 8. So at that time you will select 8 like this. Okay, so once you select 8, then this edge will also be removed. So now still 5 we cannot select because there is one edge is coming from 4, but we can select 4 because there is no dependency for 4. So after selection of 8, we have only one choice, 4. Then we can select this 4. Okay, so once we select this 4, so this edge will be removed, this 7 will be removed, and yeah, only this will be removed. Oh, okay, sorry, I missed one thing. So no, 5 is not selected yet. Okay, fine. Yeah, so this now there is no dependency on 5. Okay, so now we can select 5, but still 1 have dependency. Okay, no, fine. So after that we have only one choice, we can select only 5. Okay, when we remove this 5, so this dependency will be removed, this will be removed. Now we have two choice, 1 and 6. Okay, Now we have two choice, 1 and 6. So 1 and 6. So how we can select from 1 and 6? So we will check this preference list. So now 1 is coming before 6. So we will select 1. Okay. Now the next, after selecting 1, so this dependency will be removed. Now we have only one choice. We will move to 6. And after 6, this dependency will be removed, and 7. We can select 7. So this is the order. We can select the task. So 0, 2, 3, 8, 4, 5, 1, 6, 7. Okay. So this order you have to return. 0, 2, 3 like this. Okay. So 0, 2, 3, 8, 4, 5, 1, 6, 7. I hope this thing is clear by the graph.
Sir, why are we really going to 1? It's redundant, is it?
1 is repeated?
8, 4, 5.
Huh?
And 6 and 7 straight you can go, no?
No, but why you are left in 1? We have to complete all, no?
No. Our start node is 0, end node is 7, is it?
No, here these are the tasks, and we have to find out the sequence of the tasks we can perform. Okay, this is not a,
this task we can perform for what? To complete 7, is it?
Yeah, here we have to complete all the tasks. This is the problem. This is not a shortest path things. Okay, this is not a path. This is a sequence of tasks we need to we can perform, and this is the dependency based problems where some tasks are given, but dependency is also given for the task. That means one task. So maybe one task is dependent on another task. So that means you cannot complete that current task without completing the dependent task. So,
for example, 1. Let's really pick up the case there. 1.
What 1?
Can you please go to the graph?
Yes.
Okay. Now, 4, 5, 6, and 7. Okay. And why are we going to 1 here? From 5 to 1.
Yeah. Okay. So when we at this 5, okay, when we complete this 5, so that means 1 and 6, we have two choices, because now there is no dependency for 1. All the dependency are completed.
Can I not read that one as for completing the task 1, I should complete 5. And similarly for completing the task 6, I should complete 5, is it?
Yeah, this graph is actually representing the dependency. You cannot complete this 6 without completing this 5.
Correct, that's right.
Yeah.
But okay, you mean to say that I cannot complete 7 unless I complete 1, 4, and 6, is it?
Yes, correct. This is the dependency. This direct edge is representing the dependency. That means we have to complete all the previous vertex where from we are getting the edge to complete this.
Okay, in the shortest path we are just ignoring.
This is not a shortest path. This is totally different problem. This is not a path. This is a sequence of steps.
Okay, in the shortest path problem, we are not at all bothering about dependencies. Eh?
Yes.
We are just reaching the target.
Yeah, correct. Okay, here we are not getting any start and last vertex. Okay, here we can start from the node which not contain the dependency. Okay, and then we will just find out the steps. So here there is no target or there is no destination like this.
So how do we say here when is the tasks are completed? Is it not that 7 is the completion point?
Yeah, 7 is the completion point for this problem. Yeah, correct.
Okay.
But this is not always the case. Okay, this is depend on the graph, how the this graph is created actually. Okay, so
all right.
And this graph is actually called the DAG, directed acyclic graph. Okay, so here there is no cycle actually.
Or it should be where it is given.
This is given in the problem, no?
That is given in the problem.
Yeah, this is this adjacency list is given. Okay, this adjacency list is given, and this adjacent. So this actually problems is actually asked only for the DAG. This directed acyclic graph problems.
No, that is what I am missing, sir. Where is it that is a DAG? What really?
No, it is not written, but by default, if this type of dependency-based problems can be asked only on the DAG.
Why? Why not on the DAG? Why not on the...
Because so suppose we cannot create the cycle. Suppose if I create the cycle in this graph, okay, let I create the cycle. So this is not, now this will not create a dependency problems. So how? Okay, if this cycle is given 0 to 2 and 2 to 0, then you cannot complete the both problems.
You will be looping there. You will never get out of there.
You cannot select any problems now, because 0 have the dependency on 2, 2 have the dependency on 0. Then how you will select the vertex to complete?
Oh, okay. The cross dependency really makes us to loop around that.
Yeah. So because of that, this dependency types of problems can be applicable on the DAG, directed acyclic graph.
So just one confusion. DAG means it can be achieved through your BFS and DFS also.
No.
Yes, sir.
So this is not a shortest path or this type of thing. This is different algorithm, topological sort, which is covered in the Big 4. Okay, here actually we are just finding out the things which we can select first, and after we will remove the dependency, then we will select. Okay, so according to the algorithm terms, what we will do, so this is the just application purpose. Okay, so how we are selecting the things after complete one steps, so we will remove all the edges which are going from that. That means dependency is completed, then we can select anything. But algorithm wise, how we will just perform these things, so we will just note down the in degree. This one in degree things, I hope you know the in degree and out degree in the graph. So suppose this is a graph. Okay, so 1 and this one edge connected like this. So what is the in degree of 0? What is the in degree of 1? What is the out degree of 0? What is the out degree of 1? So
in degree of 1 is 1. And 0
so
in degree is 0.
Yeah, what in degree is represented? How many edges are coming on that vertex? Okay, out degree is represented how many edges are going from that vertex. Okay, so in degree for this, if I represent in degree for this 0, so there is no in degree, that means 0. Okay, out degree is for is 1. This one edge is going from this 0. Same for in degree for this one vertex is 1. Out degree equal to 0. So this is the in degree and the out degree information. Okay, so this in degree, actually this in degree we will use to solve that problems which I have just explained in this graph. So in the initial graph, so this is the graph. So how we will solve this problem? So if you see the topological sort algorithm, so what concept we are using to solve the problem? So first things, we will calculate the in degree for all vertex. Okay, so if we just solve this problem graphically, so what is the in degree of 0? 0. Okay, there is no in degree. Now what is the in degree for 2? How many edges are coming on 2? Only 1. Okay, what is the in degree for 3?
2.
2. What is the in degree for 1?
3.
Correct. What is the in degree for 7? 3. What is the in degree for 6? 1.
1.
What is the in degree for 5?
3.
What is the in degree for 4?
1.
1. What is the in degree for 8?
1.
1. Okay, so this is the initial steps. First step, after receiving the graph, calculate the in degree for each vertex. Okay, after that, how you can process? So you can select the vertex which have in degree 0. Okay, which have in degree 0, you can select only that vertex. So in this data, definitely you will maintain some dictionary for this information. Okay, so this 3 all in degree information. You can maintain any dictionary. So you just check that in the dictionary or list where you are maintaining the data, just check that which vertex contains the in degree 0. In degree 0 means there is no dependency for that node. So you can just select that node. You can just remove this node from the graph, and you can consider this as a first step, first removed node. Okay, so this 0 will be removed first. So after removing this, okay, once you just remove this from the graph, there is no need to remove from the graph actually. Just update the in degree information for the remaining node, and also you can mark this as a visited. Okay, you can mark this as a visited or removed, any condition. You can take any data for this. After that, so once you are complete this dependency, that means you have removed this. Just reduce the in degree of the node where the edge are connecting from this removed node. Okay, so once you remove this node from the graph, so just reduce the update the in degree. So edge are, so where what are the adjacent of this 0? So adjacent of 0 is 1,
2,
3,
1.
and 1. Okay, so 1, 2, 3. So just reduce the in degree by 1 for each adjacent. Okay, so this will become 0, this will become 1, and this will become 2. Okay, now this is the updation. Once you have visited this node, this is the updation in the graph. Same things repeat again. Now select the node which have in degree 0. Okay, suppose if any time you are getting the in degree 0 for more than one nodes, at that time, according to the problem, just read this preference. One preference list is given. Just check that which vertex is coming first in this list. So this preference is given. This first node is have the highest preference, last is the lowest preference. So at any time when you are getting in degree 0 on more than one vertex, to select the node, just check the preference in this list. Okay, then select that node. Okay, so in this example, we have only, you can see only one vertex which have in degree 0 now. This is 2. Okay, now you will select this node. This will be selected. Okay, once you will select this, same things you will check the nodes which are not visited and what are the adjacent node of this 2. Okay, so adjacent node of 2 is 3 and this 5. So just reduce the in degree of by 1. Okay, so now it will reduce to 0 and this will be reduced to now 2. Okay, now this node is also disconnect complete. Same things repeat again. Now check which node have the in degree 0. So now 3. Okay, so you can select only 3 here. So when you select this 3, all the adjacent nodes, so 3 to 8, 3 to 4, 3 to 1, just reduce the in degree. Okay, so this will become 0, this will become 0, and this will become 1. Okay, now after that you can see here 2 vertex have 0 in degree, so this 4 and 8. Okay, so at that time just check the preference list. So 4 and 8, which vertex is coming first? So 8 is coming first. Okay, so
how are we going to check? Means like there are 2 vertices and we have to check, like how will we check that 4 is coming before?
So you can just calculate, find out the index now. Okay, in list you can check what is the index of 8. Okay, you can just collect the index of each node, and you can make the tuples for the index, this information. What you can do, just you can find out the index for this 8 and 4. So just make the tuple and maintain the index at first position. Okay, so what will be the index come at the 8? 0, 1, 2, 3, 4. So 4 and 8. Okay, this is the first. What is the second node? Is 4. So what is the index of 4? This is 5, 6. 6 and 4. So these 2 tuple you will get, then apply the sort in this list. Okay, so you will get this 8 first, then just remove this. Okay, so in this, in this manner you can select, you will select 4 now. So you will select 4. Once you select 4, check the adjacent of 4. This is now 5, will reduce 1, and there is 1 4 to 7, just reduce by 1. Okay, 2. Now you can see So this is also I mark as the visited node. Okay. So now just see the degree in degree of each node, remaining node. So you can see only 8 is remaining. Okay, so with 0 in degree. So now you can select 8. Once you select this 8, then the this 5 in degree will reduce. Okay, so this will become 0. So after that, you can see only one node have in degree 0. So you will select only this 5. So when you select this 5, 2 adjacents are there which are not visited yet. So this will become 0 and this will also become 0. Now once again 1 and 6, you have two choice. So same things, 1 and 6, you can see 1 is coming before 6. So you will choose 1 first. Okay. Now when you select this 1, this will be reduced to 1. Okay. Now you have only one choice to select 6. Okay. When you select this 6, then this will be reduced to 0 and you can select 7. Okay. So you can find out the path in this manner. So if you see the topological sort, I'm just explaining the topological sort in the implementation part. Topological sort. So you have to update little bit. Okay. So in the problem, so same things what we are doing, this topological sort, we are maintaining one queue, and you can see in degree and topological sort we are maintaining some dictionary for in degree here. Initially we are assigning in degree, we are initially this in degree 0. Yeah. So this is initially we are assigning in degree 0. After that we are updating the in degree for all vertex. So you can see in the second loop, compute in degree for each vertex. So this is the initial steps. First we are computing the in degree for each vertex. After that we are selecting the vertex with in degree 0. So you can see that in the all complete, we are just finding out the vertex which have in degree 0, and we are appending all the vertex in our queue. Okay. Here actually in the previous problem, if we are getting more than two vertex with in degree 0, then we are selecting based on the preference list. But in general, we just select based on the queue. We can take any queue and we can insert all the vertex in the queue which have in degree 0. So based on the problem, you can just update little bit. So here, this is the key. We are inserting all the vertex which have in degree 0. Then we are repeating the same process again. We are removing one vertex from the queue. This is current vertex. After that, we are appending that vertex into the topological order, and we are reducing the in degree of this selected vertex by 1, and also we are reducing all the adjacent in degree by 1 by this loop. Okay, and we are repeating this process again and again till the last node. So if you see this algorithm, then you can directly use this topological sort approach to solve the last problem.
So using that code, we can get our topological sort list, and after getting that list, can we sort our list according to this preference, like in code?
No. So every time actually we are not selecting based on the preference. We are selecting the preference list only when we are getting more than 2 node within degree 0. So that things will not work, which you have said now. Okay, so that may be written the incorrect data. So you have to update the code. This you have to use the same logic here, but here actually we are using one just 0 degree in this queue. So there is no need to take this 0 degree queue. Okay. So at the time when you just collect the all vertex which have in degree 0, and at the time just find out the vertex which have highest preference from the preference list. Then do this process repeatedly. Okay. So which you have just said that after selecting the order, then based on preference list you will sort that. So that I think will not work. Okay. Yeah, preference list is only used when we have more than one choice.
Okay, sir.
Okay. So just use this algorithm with to solve this problem and just modify a little bit according to the problem. You will get the answer. So I've already explained the.
Sir, I don't think that's a little bit modification.
No, this is a little bit modified, not too much.
Yes, sir, but the logic means to
This
get the logic
actually,
is
yeah,
very
logic is actually similar, but you have to write the code for this part. When you have more than two nodes with in degree 0, you have to find out the.
like I understood the logic, but when the nodes were equal and I had to sort for the then you have explained it, but there was the point where I got stuck that how do I select from this list that which ones are which is coming first, and like I can see it.
Because of that I have just explained it. You can make this type of tuples and you can directly apply the L dot sort. So list will be sorted based on the first value of the tuple. So this first value is representing the index. Okay. So definitely the element which is coming at the initial, it will come as the first position. After that you can just remove, read that element as for the process. Okay. So that part you have to add in this code only, this preference part. Otherwise this is totally the topological sort. Okay, so regarding in degree, I've just mentioned you can just follow this topological sort algorithms. Just try it. Okay, if you're finding difficult to this, you can discuss in the next week also. Okay, so these three problems are actually the OPP problem which is asked previous terms in the initial terms, not okay. But for the OPP problems, just definitely one problems will be come from week 4 and 5. Okay, graph where the algorithms, basic algorithm knowledge is required. Okay, so this BFS, DFS, topological sort, and shortest path algorithm and minimum spanning tree algorithm. So just learn these 5 algorithms conceptually. Okay. Yeah, any query? Any query?
No, sir.
Okay.
Thank you, sir.
Okay, just complete these problems by your own. Just write the code by your own. Okay.
Yes, sir.
Okay, so next week actually we are just scheduling 3 revision session by the TA. Okay, so that Monday, Tuesday, and Thursday. That session will be by the TA. The session will be recorded but not live stream. So just join the session. Okay, and these Monday will be covered for week 2, and Tuesday for week 3, and Thursday for week 4. And we will conduct one revision session on Friday. Okay, so we will revise all the week's main important things. So also join that session. Okay, we'll discuss important questions which can be asked for each topic. So please join.
Sir, sir, if we are having a session on Wednesday and Friday that for revision, so for week 5 it will not be there.
Yeah, week 5 we will discuss on Wednesday. We will not skip that. Otherwise, it will difficult to cover in the next week in the both.
Like there will be two separate sessions, or in one session you will discuss both things.
One session for quiz 1 we will conduct only one revision session, and TA will conduct 3 revision session for each week separately: Monday, Tuesday, and the Thursday.
Okay. So what will be the timing?
TA session timing are 8:30, Monday, Tuesday, and Thursday, and in the next week we will not conduct the live coding session for week 6. Sorry, week 5. We will conduct the revision session. It's the same timing, 8 p.m.
But there is one week 5 scheduled, sir. Are you going to have that?
Yeah, week 5 open session will be scheduled in the next
But
week.
why do we have that one now? Why don't we really push it back?
No, actually we cannot push to the back. Otherwise, we have to push one for the quiz 2, then one for the OPP. Then how we can cover all the things in the given timeline?
But do you think it really work when we are all busy?
We will conduct the session on next Wednesday for week 5. If anything is remaining, if you are not able to understand anything, you can discuss in next week also. Okay, but we will not skip this session, week 5 session.
Okay, sir. Okay, thank you.
And live coding we will combine in the week 6. So week 5 and week 6 will combine in the next week. Okay.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thanks. Good night, everyone.
Good night.
Good night, sir.
Yeah, good night.
Good night, sir.
Yeah, good night.